Hello everybody, it's Professor Fiore, and today's hot topic is resistive sensors. There's been a lot of discussion lately about intelligent machines, things like self-driving cars, or maybe a rover on a distant planet that's moving around independently, autonomously. But we could even go to something as simple as a device that might, let's say, turn on your headlights in your car when it's dark out automatically. Or maybe you have a greenhouse, and if it gets too hot in there, your tomatoes and your peppers are going to wilt. So we want something that will turn on a fan, an exhaust fan, if in fact it gets too hot in there. We like these things because otherwise we have to do it ourselves. I don't want to hang around the greenhouse and then look at a thermometer and say, yeah, it's too hot in here. I got to turn the fan on. Oh, seriously? I would just rather have some device do that for me. Well, ultimately, we need devices that are sensitive to certain environmental cues, so to speak, certain parameters, and we want to turn that into a voltage. It might be really complicated, something very advanced, like a radar ranging system or a high resolution camera that we're going to do some digital signal processing on to find various items in that field. But it can be something much, much more simple. And that's where we need to begin. So we are talking about resistive sensors, devices that look at some particular environmental characteristic like maybe temperature or humidity, something like that. Light could be many different things. And its resistance changes in accordance with that. There's some kind of relationship between these two things. Ideally, we would like this relationship to be repeatable and accurate. But sometimes we just need a gross change. It all depends on what we're doing. So we're going to look at three things. We're going to look at thermistors, light-dependent resistors, and force-sensing resistors. So here's the first one, which is a thermistor. So this is a temperature-dependent resistor. That's the way to think of it. They come in two types, an NTC or a PTC. Those are negative temperature coefficient and positive temperature coefficient. So what I have here is an NTC, negative temperature coefficient. So here's a graph that shows what's going on with its resistance. You can see this is kind of looks like maybe a tantalum capacitor, maybe like a little tiny resistor. And this is typically smaller than your standard run-of-the-mill, quarter watt resistor. But you can see what's going on with this graph here, right? We've got a resistance starting down here at 1 ohm, going all the way up here to 10,000 k ohms. I believe I said 1 ohm, I meant 1 k ohm here. So it's a pretty big range across this temperature run. So we're looking at the bottom of the graph is negative 50 centigrade. They're only plotting out not quite to there, and then on the top end, we're going up to 125 degrees centigrade. I do want to point out one important thing, right? Besides the fact that this is negative temperature coefficient, meaning the slope of this is negative. As the temperature goes up, the resistance goes down. The thing I want to point out is the axis, the resistance axis over here is a logarithmic axis. This is not a linear axis. For the temperature, each of these major divisions is 25 degrees, right? 25 centigrade degrees going up. But for the resistance, what we see is factors of 10, right? 1, 10, 100, 1,000, 10,000. So, down here we've got k ohms, up here we've got mega ohms, right? And this is not a perfectly straight line. Right? There is a little bit of curvature here. But what is important is over a very wide temperature range, certainly beyond anything humans would consider comfortable, right? Or your tomatoes for that matter, we can get a sizable, many orders of magnitude change in resistance. And we'll be able to use that to create some kind of voltage that represents a temperature. Now, the positive temperature coefficient version of this, basically the curve goes this way. There's a positive slope, right? It's going uphill instead of downhill as you go from left to right. There are some other differences there, but we're just going to leave it. This is just a basic idea. Remember, temperature goes up, resistance goes down. That's the way this works. Okay. Next thing, light-dependent resistor, an LDR. These are commonly built with cadmium sulfide, so you'll hear them referred to as CDS cells, right? CD is cadmium. Cadmium is maybe not the best material to be futzing with. It's in that same category of like, lead and mercury. ROHS restrictions on this, but these are commonly used for sensing light levels. So down here we have that same kind of graph we just saw with the thermistor. So lux is the intensity of the light. You can think of that as how many photons are hitting the surface in a given period of time. And then we have a resistance. This is also logarithmic. This is doubly logarithmic. This is a log-log graph, right? So here we're going by factors of 10 for the light intensity from 0.1 to 10,000 lux. And we see the same sort of thing happening with resistance, right? This is in k ohms, so we got 100 ohms down here, 1,000, 10,000, and up we go, right? So we're looking up here at 1,000 kiloohms, a megohm. So as the light level increases, right, as it gets brighter and brighter and brighter, this resistance drops. And again, we'll be able to use this for any number of things that are sensing light. We could put lenses on this. There's various things we can do. We can just leave it as it is. Commonly, you will find these in old night lights that you might put in your house. They have a little incandescent bulb in there. You'll see a little sort of lens on the front of it, and behind it will be a CDS cell, so that when it gets dark in your house, the resistance changes, right? When it gets dark, this resistance goes up, and we'll use that to trigger a circuit which turns on the light, right? Because, you don't want to get up in the middle of the night and stub your toe, so we got a little light going on there. And you don't want to have to turn it on and off every morning and evening, so, right, it's sensing. It's a very, very simple intelligent machine in that regard. It is sensing its environment. It is important to note that a light sensing device is not equally sensitive to all wavelengths or all colors of light. So very often we'll get a spectral graph. This goes from 0 to 100%, so its most sensitive wavelength will be 100%, and then we can see what's happening here. And this particular unit, we're getting a peak somewhere around 540, 550, 560 nanometer wavelength. This peak, depending on where you define it beginning and ending, is sort of in the green-yellow area. It's not super sensitive to longer wavelengths. Okay, the items up here, we see it just sort of dropping down, or shorter wavelengths, ultraviolet versus the reds, the infrareds. But this is smack dab in the middle of the human visual range. So, it works well. And this is not the case for every single cadmium sulfide cell. You'll find that different LDRs have slightly different curves, but you will find generally this kind of shape, right? There is a sensitive area that it will pick up. But if all you're looking for is, hey, is it bright outside? If the sun's out, okay, the sun never turns its light solely into blue or green or red. It's a mixture of all those different wavelengths. Right? So that works well enough. Next on the hit parade, we have an FSR, a force sensing resistor. These come in different shapes. You will find these to be maybe about the size of a coin, like a penny, maybe a little larger than that, a couple of centimeters across, different shapes. Round and square are pretty popular. You also see some sort of long rectangular shaped units. And basically this is sort of a sandwich. There's two layers on here, and as force is applied to it, so this would be affixed to a surface, as force is applied to it, the resistance changes. You could kind of think of this as one surface making better contact with the other surface. And in so doing, there's greater conductivity. So a simple plot of this is using a linear graph here. I've got the force in kilograms going across the horizontal, and on the vertical we have the resistance in ohms. And you can see this is a rather abrupt change that we have, but there certainly is this decreasing resistance as the force goes up. If you plot this on a log-log graph, which is down here, so this is going to the same point. This is 10 kilograms. This is 10,000 grams, right? We're going to the same point. You get kind of a straight line. You get something much closer to a straight line. You'll see little squiggles and whatnot in it. But there is a pretty big change in resistance, right? So for really no force, if it's just sitting there free, in this case, we're getting something in the 100 k ohm plus. But if you put a lot of force on it, you really lean into it, we're down here, right? This is 0.1 k ohms. So we're looking at maybe a couple hundred ohms. So you would use these things for user interface. If I want to actuate something, the user comes by and I want them to just sort of press a button, but I don't want a mechanical button, something that's going to break, just something that I want to push on, sort of a yes-no kind of thing I want to select. But it can be used for analog control. You could use one of these things, for example, on a synthesizer, so that when you press on it, you get pitch shift. Now, on a synth, those are very often done with little wheels, mechanical wheels. And some other things have come up over the years where they've had little ribbon devices and things like this. But you could do something like that, an effects push button, so to speak, just a surface, and you could assign that to different parameters. Like I said, you could make a vibrato by assigning it to pitch, or maybe a tremolo effect, things like that. So it's useful because there's really no moving parts in the mechanics. Like if you think in terms of a momentary contact push button, right? And that's strictly on and off, where this is a smoothly changing parameter. So you can actually see somebody's pushing on this hard or not so hard. You have an analog control over it. So that's nice, all right? Okay, now that we've got these devices, and I will just remind you that generally speaking, they're all showing this decreasing resistance as the quantity of interest increases, right? Increasing force, less resistance. Increasing light, less resistance. Increasing temperature, less resistance. So, yeah, I know, PTCs, you can get them to go the other way. There aren't any reverses, though, for the FSR or the LDR. How do we use them, right? That's the big question. How do I turn this into a voltage? Well, the simplest thing you can do, and a quite effective thing you can do, is to just create a little voltage divider. So I have a power supply. I'm just using 5 volts here, and I've got 2 resistors. One of these 2 is going to be the sensor. And what I've labeled here is V out. It's just a voltage divider rule. So V out is your source, E times the item I'm interested in right here, right? R2, which is V out to ground. So it's R2 over the total, R1 plus R2. Now, if you have the sensor in this position, like for example, you have an FSR, let's say, as you're pushing down on it, you're getting less and less and less resistance. So the voltage divider rule would say if this resistor is getting smaller, right, that's over here in the numerator, this is getting smaller and smaller and smaller faster than this is, because you've got R1 associated with the R2 down here. So what ends up happening? Well, your V out drops. Right? Same thing would be true with the temperature sensor. Right? As temperature goes up, resistance drops. So what we see is this voltage dropping. All right. Same thing with that NTC. The light sensor, right? The LDR. As the light level goes up, this resistance drops, and we get a smaller and smaller voltage. So at this point, everybody's thinking, but I want the opposite. If there's a high temperature, I want a high voltage. If there's a high force, I want a high voltage. If there's a lot of light, I want a big voltage. Okay? Yeah, sure. Why not? You can do it that way. It depends on what you're doing. This could be perfectly useful for what you're doing, but you might want the other thing, right? You might want it to work the other way so that the voltage more closely represents the trend, what's happening with the light or the temperature or the force, right? As those things go up, I want the voltage to go up. Well, there's an easy fix. Just move the sensor over there. So if R1 is the sensor, right? So again, I'll go back to the FSR. If you push on it, then this resistance gets smaller. And if we look at the equation over here, right? R2 is fixed. I'm just going to have a fixed resistor over here. So I push harder, the sensor gets smaller resistance, R1 gets smaller, what happens? V out goes up. Same thing happens with the temperature, same thing happens with the light levels. All right? The only thing you really need to play with are the specific values of these resistors, right? Whichever one you're doing. So if I were to go back to my original here, those sensors typically on the low end, when they're fully actuated, let's say, like maximum force, high temperature, you probably are going to get hundreds of ohms, maybe a few thousand ohms. And at the other extreme, for example, with the light, if you have no light, you're going to get a large value, maybe hundreds of K, maybe megohms. So to get the best range out of this, you're going to want the other resistor, right? So in this case, the R1, to be somewhere in between there. So in this case, I've just thrown a 10K in, all right? So if I have a lot of light, I'm going to have a small resistance like 1K over here, and I'm going to get a very small V out. On the other hand, if there's no light, R2 becomes a massive value, hundreds of K, maybe megohms, in which case we get virtually all of E at V out, right? Because I only have a 10K here. So I have at least an order of magnitude on either side of that with my sensor. I don't want to put 100 ohms over here. If my sensor is varying from a K up to a meg, that doesn't make any sense. But I don't really want to put a meg over here either, because again, I'm not going to get the best sort of sensitivity. I want to put something in the middle there. It will depend on exactly what you're looking for. If you're looking for a digital kind of output, you're going to have to play with this to get the best sort of actuation depending on what level you're looking for. What is the brightness that you're looking for? What is the temperature that you're looking for? In which case, to calibrate it initially, just turn this into a pot, right? A 2-lead pot, a rheostat. And then you can sort of play with this and adjust its value, and that's where the output voltage will trigger. For example, if you had a digital circuit on here, you might have a little Schmidt trigger out here. And where that triggers, you can control with that rheostat, right? Bring that up and down. If it's a fixed sort of thing, you just have to calibrate it. Well, then I'll just measure the value of the rheostat and replace it with a fixed resistor. Off we go, right? If you want it to be adjustable, then you just leave the rheostat in there, or to sort of narrow that range a little bit so it's not so wild, so extreme, you just put the rheostat in series with another resistance, okay? And that will set a lower limit for the value of the rheostat, and you just vary between there and the full rheostat value, okay? So what I'm showing here would be typical for the devices that we've just looked at, right? With that 10K. So if I look, for example, at my LDR, okay, this is in K ohms, so here's my 10K. That's kind of the middle of the range. We're looking at like maybe 20 lux or something over there. Is that sufficient for your application? I don't know. That's your application. You got to figure that out. But you can see the range of the resistance. Similarly, if I were to look at the FSR, okay, let me use the log version over here, the log version. So, what's the force I'm interested in? How hard do I want to push? And if I'm looking at something down here, okay, a 10K, that looks pretty good. If I'm pushing pretty hard, pretty high force, 10 kilogram force, well, maybe I want that resistor to be a little bit smaller. Maybe, a 2.2K might be a better choice, right? All depends on what we're looking for, all right? Okay, but that's a simple way of doing it. Just a simple, I know it sounds like, is it really that simple? Yeah, it is. And for those of you that are using microcontrollers, this V out would simply go into one of your analog inputs. If you want to get a continuously variable measurement on something, this would go into an analog input. If you're just looking for a yes/no kind of thing, then this can go into a digital input, but you'd probably want to square that up. Hopefully you have a Schmidt trigger on the input. Because when you get right near, here's a trick when you're doing digital. When you get right near a trip point, you can have a little noise in there and the thing is going to chatter. It's going to go on, off, on, off, on, off very rapidly. And if you feed that into something like, let's say, that fan that was in your greenhouse, you're going to be turning that fan on and off, on and off, on and off, right around that one temperature. So you really do want something like a Schmidt trigger in there, right? Something with hysteresis so that you don't get that effect, all right? But if you're doing analog control, like for example, you want to control the speed of the fan with the temperature. When it gets hotter, you want the fan to go higher. Then yeah, an analog input is perfect for this, okay? All right, there are other kinds of sensors out there, but this gives you sort of an introductory idea of what's available and what's out. And really, it's kind of fun to play with these things. You know, you can buy them really cheap. There's, you know, a billion places you can find things like FSRs. And of the group, the FSRs are probably the most expensive, but you know, you can find cadmium sulfide cells and things like that fairly cheaply. And you can, you know, play with them on a little breadboard. You know, you can get a little flashlight, things like that. And you can control small devices. You know, if you're programming an Arduino or something like that, you can have a lot of fun, right? Just messing around with this stuff. So ultimately, this is sort of, I like to think of it as like a one brain cell brain, you know. They can kind of look at one thing, right? If you treat it digitally. If you treat it analog, continuously variable, well, maybe there's a few more brain cells in there, right? In our little intelligent machine. Okay, great. So if you have any questions, put them down in the comments. We'll see you next time. Bye-bye.